we have a fun, exciting end to section 1.8 on linear differential equations. It's fun because we're going to look at pictures to start, and then we have some wild wackiness happen. So if you remember, we did 2 example problems over here. We're going to graph those example problems. They had the same homogeneous, like associated homogeneous differential equation. They just had a different right-hand side. So if we look at those, let's pull up our slope field. If you look at this first one, we got a bunch of different solutions on the left, but you can see that as time passes, all of the solutions kind of merge together, right? And they all kind of approach an exponential function. Now, if you look back at that first equation, the solution, oh yeah, as time goes on, right? As time goes on, this is going to 0. So of course all the solutions are going to approach that particular solution. Yeah, that makes sense. And if we look at the other one, yeah, we got wild oscillation from all sorts of places, but eventually we settle into a groove. That groove is called a steady state solution. Okay. And again, what we have here, we can see the same thing, right? This part's going to 0. And eventually, the first part's 0, so we're eventually just here, we have a periodic function. All right? So again, we're going to make an observation based off of that with a little bit more qualitative analysis. So in that second example, right, approaches, this is an important word term, a steady state solution. And that means something different in different contexts. So we're not going to get too precise in our definition for it. We're just going to say, they approach, right? All solutions approach the particular solution as t goes to infinity, which, oscillates periodically. All right, and that's what we'll kind of think of as a steady state solution, but in different disciplines, it can mean something a little bit different. Okay, and that's mostly what the book is focusing on here. So we have a steady state solution for the second example. The first one's not a steady state solution because even though they merge to the particular solution, it's an exponential function, not steady at all. Okay, but the second one, again, first one goes to that exponential function. Second one, they all settle into that groove, that oscillation. That'll be our steady state solution. Even though things change, they all change periodically, right? It repeats. And nothing crazy happens, basically. So let's kind of try to wrap this stuff up in a nice little bow. So let's consider a constant coefficient linear differential equation. We could go all the way back to the first video to remember what that was, or I could just tell you dy dt equals lambda times y plus b to the t. And remember the homogeneous solution, well, hold on, let's not give you the answer before I ask the question, all right? When do we know that all solutions approach yp as t goes to infinity? Is it all the time? Is it only for some lambda? Or what? And to answer this question, we kind of have to think, well, what does the homogeneous solution look like? The homogeneous solution is going to be a solution to this, right? That's just going to be k e to the lambda t. And we said the reason why they all kind of approach that same solution is because the homogeneous part was going to 0. So when does this go to 0? This goes to 0 when lambda is negative, right? So we're going to say when lambda is negative, all solutions to the non-homogeneous differential equation approach one particular solution. All right. And that's all the qualitative analysis we're doing in this video. Oh. Oh. I went out of order. Anyway, so let's jump into the next part, and that's going to be second guessing. What is second guessing? You're going to find out. We'll stumble upon it. Let's do a problem, a totally innocuous problem. Nothing bad's going to happen. dy dt plus 2y equals... Nope, we already did that one. Oh, it is the same. dy dt plus 2y equals 3e to the negative 2t. And you might say, Jason, this looks boring. We already know the homogeneous solution. You've given it to us a million times. The homogeneous solution is just ke to the negative 2t. Blah, blah, blah. So boring. And Jason, we already know how the particular solution is going to look. We know the particular solution, our guess, right, is that it's just going to look like alpha times e to the negative 2t. And, okay, I guess it's good practice, but let's keep going, right? What is the derivative of y with respect to t for this y? All right, that's going to be negative 2 alpha e to the negative 2t. We don't forget our chain rule in this class. I never have myself. Plus 2 times y, which is this. All right, and we want this to equal 3e to the negative 2t. So we're going to simplify the left-hand side and then solve for alpha. When we add these two things together, we get negative 2 alpha plus 2 alpha equals... Huh. Well, that's not true. I don't care what alpha is. This isn't true. Well, what happened? I'm sure you're not at all surprised by the fact that something happened. But what happened? Well, what happened, right, is our homogeneous solution looks exactly like we guessed. We did not make an educated guess. Our homogeneous solution looked exactly like our guess for our particular solution. It's never going to work. It can't equal 0, which is the homogeneous, and this. We're doomed to fail. I set you up for failure. But don't worry, I will also give you an opportunity for success. So we need to modify our guess. We need a second guess, if you will. All right, so let's modify our guess because it's still pretty much a good guess, right? We just still don't want sines and cosines. That will still never work. We still don't want polynomials. That'll never work. We still don't want e to the 3t. We need to have an e to the negative 2t in our guess. But we don't want things to cancel out to 0. Remember your product rule. What if we guess something a little different? What if we guess alpha times t, e to the negative 2t? Well, now when we take the derivative, we'll have two terms. One will have a t, one won't have a t. The one with the t is going to cancel with this one. So we've tricked the problem to we know we're stuck with cancellation. But because of here, we now have product rule giving us something that won't cancel. All right, and if this doesn't work, like if there was also a t over here, we could do t squared. And if that didn't work, if there was also a t squared, we could do a t cubed. We could do all sorts of fun guessing, third guessing and fourth guessing and fifth guessing. We're probably not going to do that, but we could. So now what happens? Right? Again, we want dy dt plus 2y to equal 3e to the negative 2t. Our new guess, right, is alpha times t e to the negative 2t. So we take the derivative of that with respect to t. We need the product rule, right? Here's our f, and here's our g. We know we should have f prime g plus fg prime. And when we do that, f prime is just alpha times g e to the negative 2t plus f, which is alpha, alpha t times g prime, which is negative 2 e to the negative 2t. All right, and then we still have the plus 2y from before. What was y? It's all of this stuff. And again, we want this to equal 3e to the negative 2t. And we'll simplify and we'll get something interesting, but the most important thing, right, is that, oh, yeah, negative 2 alpha t e to the negative 2t and positive 2 alpha t e to the negative 2t, and they cancel out. So we have alpha e to the negative 2t equals 3e to the negative 2t. I can solve that equation, no problem. Alpha is equal to 3. All right. So we get a particular solution is 3t e to the negative 2t, which is fantastic. We could check our answer, or we could just move on to get our full solution. It's our our homogeneous solution, our general homogeneous solution, which is ke to the negative 2t, plus any particular solution. We found one of 3t e to the negative 2t. And we could check our answer. We could take the derivative of this. We'd see everything checks out just fine. And we've got it. We did it. And again, if you don't like all this guessing, you're not alone. Most math people don't. And we talked more about like how to do better guessing in 1.9, how to get away from guessing. We also talk about it a little bit in Appendix B, which we'll talk about, I believe, after Chapter 1. I have to check my course map again. But yeah, we talk more about how to not guess and how to do better guesses later on in this book. So stay tuned. Be on the edge of your seat. Count down the days. Anyway, that's it for this section. Again, qualitative analysis. There are some conditions for constant coefficients that will lead all of your general solutions to approach a particular solution. And then also, sometimes first guessing doesn't work even if you guess the best. We can do second guessing. A lot of times this could, if things all turn out to be zeros, we can add a linear term or a quadratic term or it's so on, okay? And yeah, use this as a model in your own guessing. Take it easy. Good luck. Study hard. Do lots of homework problems. Do extra problems. Watch extra videos. Ask questions. Go to office hours. Send emails. You have my permission to do all of those things. And take care of yourself. Bye-bye.